Hi, and thanks for tuning in to the CBA Podcast, a place where we chat about our own recent achievements in the area of electronics, software and mechanical engineering, and more likely than not, give excuses for not having done anything at all. Hello, welcome back to another episode. As a matter of fact, I'm not using my PC to record the podcast as usual, but I'm using my cell phone, so let's see how that works out. I got a small adapter cable to connect my normal standalone fancy pants microphone to my cell phone, so I think audio quality is okay, but we'll see later. And talking of editing, I like to listen to podcasts while I'm in the car usually, and one of these podcasts is Eaten by a Gru, I think I mentioned that before, by Carrington Vanson and Kevin Savitz. And that podcast is not about technology, it's about Infocom, adventure games, but each episode is about 1 hour, and just out of interest I asked them how much time they normally take to edit one episode, and they said, well, we don't take any time, we just record it and put an intro and outro edit against it, with it, and then send it out the door. So if I compare it to myself, this is a 15-minute podcast, 10 to 15 minutes, and sometimes I spend 1 hour, 1.5 or 2 hours editing, so it's a bit ridiculous. So I'm trying to do it a bit faster and once again limit the amount of editing I have to do. First actual thing I did was not very impressive. For the TS100 portable soldering iron I got recently, the tip that came with the soldering iron was a TS-B2 tip, which is a small conical tip, and I think for general purpose tip, conical tip doesn't make sense because it has very poor heat transfer. You only use it in very specialized cases I think. So I tried to see what was available locally, and the only thing they had that was appropriate, I think, was a TS-C4 tip if you're playing along at home, which is a hoof-shaped tip, and that was much bigger. But I like hoof-shaped tips as a general purpose tip because you can do a lot of things with it. You can use a tip, the sharp end for SMD work, and it is quite big, so it has quite good heat transfer, and it's a nice general purpose tip, but whatever works for you, but I'm much happier with this one now. Tested it and it's excellent, it's a nice thing. By the way, it's quite hot now and I think I have a cold or something like that, so I have to cough all the time, so I think no editing effort is not going to happen this time. Anyway, small update about something I talked about last time or the time before, was making electronic prototypes using copper-clad PCB and hand milling isolation slots out of that with a Dremel tool or something like that. Now the previous time I used a bowl-shaped milling bit, and although you have a lot of control over it, it doesn't slip away of the PCB. You can mill out isolation slots quite easily, except the isolation slots are quite wide, 1 millimeter or 2 millimeter wide. So that's fine normally, except this time I wanted to use a 0.65 millimeter pitch IC, and that was clearly not capable of doing that. So use a milling bit that came with a small benchtop milling machine, very sharp edges, and by using that tool, that milling bit, 45-degree angle to the copper surface, you can mill out very, very narrow slots. So that IC worked fine, that PCB worked fine. You don't have a lot of control over it, and you have to be a little bit careful, I guess, because the milling bit doesn't really care if it's milling copper or your finger. Time ago I got a small, cheap MP3-player, 13 euros, and it was another piece of crap. Couldn't read the SD card, the software was crap, so I returned that. I got a new one instead, 25 euros, double the price, but at least this one works. It was a strange thing, because supposedly it's some kind of waterproof or splash waterproof. You can use it in the shower, I guess, or in the bath, or while swimming, no idea. But the weird thing was that just one socket, 3.5 millimeter audio socket, and it was used for headphones and charging using a USB charger or PC, or use it as a USB mass storage device by connecting to a PC using a supplied adapter cable. So I never saw that before. I did a little bit of measurement on the adapter cable, and it seems that the USB data plus and minus are connected to audio left and right. So and the USB plus and ground are connected to the microphone and the ground of the audio socket. So I guess it senses if there's a voltage coming from the host, from the USB charger from the PC. If so, switch to USB mode, and disable the audio amplifier, and if it's not seeing a voltage, then assume you're playing audio and enable the audio amplifier and output the audio. So took a look inside, and there were only a few things, namely a lithium-ion cell, a flash, and one single chip. And it was a Actions ATJ3315, if you're playing along at home, which is a integrated audio chip for devices such like this. There's a lot of stuff on board. So charging of the cell, of the lithium-ion cell. There's a Z80 compatible core, audio decoding, USB mass storage interface, general purpose IOs, a lot of stuff. DC-DC converters, everything. So it's a very nice chip. Actually, it's also capable of recording audio using a microphone input, but that was not used on this thing. So that was that. So one thing I actually did do was go to the cheap ass store here. It's called the Action Store. They have all kinds of cheap stuff and also household stuff, but also gadgets. So I was looking for a LED-strip. Maybe to make something for the upcoming EMF cam, some nice light effect. So what I saw was what was advertised as digital RGB LED strip, €13, 5 meters, 30 LEDs per meter. It had a small infrared remote control and a wall wart power adapter for 12 volts. So I wondered what does a digital mean. So I looked at the strip, and indeed there were small ICs placed every 3 LEDs. So every 3 LEDs corresponded to one IC. And I wondered if this was a WS2811 chip, which is a serial PWM constant current 3-channel LED driver. That's quite common. So I took the chip home, looked at it under the microscope, and indeed it was that chip. So that was good, because back in 2013 I already made a little bit of software to drive these things. So that was a quite cheap way to make very nice effects then. So ignored the infrared remote control a little bit, but looked at the control box that came with the LED set. And was nothing more than a single microcontroller, I think. It was labeled MCU on the PCB. It was a little 8-pin SOIC device. And ran off a Zener diode power supply from the 12 volts, and they even used one capacitor on the board, so yay. Now a little bit more about these WS2811 chips, and also you can get the WS2812 version, which is the controller integrated in the RGB LED die. So you have a 4 or 6 pin LED package with serial communication to it. So what makes these chips nice is that they can be cascaded. They have a data in and a data out, one single pin, which is clock and data. How it works is from the host you send a data stream containing the colors for every LED in your strip, in your cascaded LED strip. And the first chip, as seen from the host side, takes the first color data from the stream, uses it for itself, and passes the rest of the color information, so for pixel 2, 3, 4, 5, and 6 on to the next chip. The next chip takes the first color information coming in for itself and passes the rest, so that would be color information for pixel 3, 4, 5, 6 on to the next chip, and so on. Each chip has data reshaping, so you don't have to worry too much about the data signal degrading after after being passed through so and so many chips. So that's how you would use a chip in a system, or how you would build a system with each chip, so cascade them into a LED strip, for example. So let's look at one individual chip. So it has 3 8-bit PWM channels, so to give it color information you would have to send 24 bits of color code into it. And data and clock are combined into one line, so what each bit looks like is a rising edge on the data line, let's say that. And depending on where the next falling edge occurs, if it's close to the rising edge or far away from the rising edge, the bit is interpreted as a 0 or 1. The chip can run in 2 modes, low speed mode and high speed mode, which is configured by a resistor. You can pull up a certain pin or not pull it up, and if it's pulled up it works in high speed mode. If it's not pulled up it works in low speed mode. And high speed mode states that the short delay between rising edge and falling edge should be about 250 nanoseconds, and the long delay between rising edge and the next falling edge is about 600 nanoseconds. And the following load time is such that each bit takes about 1 or 2 microseconds. So in the software that I already made a while ago, I read the datasheet and I did my best to make the high times of the 0 and 1 bits match what was stated in the datasheet, but also the low times. So there should be a maximum time between two adjacent bits. But when I looked at the data stream that the control box that came with the LED strip spit out on the scope, that looked completely different, because between two bits there was 10 or 12 microseconds delay. Seeing that, it seems that the delay between two bits is not important at all. So I don't know how well this scales to different versions of the chip, but to be honest I don't care, because I wanted to make something with this particular LED strip. So that makes it much easier to generate software that controls these LEDs, because timing is not so critical then. For testing this kind of stuff I usually use a AVR microcontroller, and for this test I disabled interrupts and just did the I/O using bit banging from a I/O pin. And that worked fine. However, if you're doing this kind of stuff from a system, from a chip that uses interrupts, for example for timing or doing other time critical stuff, you cannot really use bit banging. So what you can use is, most of these AVR microcontrollers have a built-in UART or a built-in SPI port. Now if you look at the SPI port, it can run at, I think at most chips operating frequency divided by 2. So I think if you want to use SPI to control these chips, and you want to use a AVR microcontroller, 8 MHz is the minimum clock frequency you can use for your chip, because your SPI port would run at 4 megabit, your bit time would be 250 nanoseconds, and that's exactly the resolution you need. I think you can also use a UART if you can configure it by software, from software to run at 4 megabit. You would need some kind of inverter behind it. You would need a start bit as a high pulse, and send, well, a 0 character basically for a short pulse, and some other character for a high pulse. You would not send a stop bit. So I think that would work. So if you look at the frame rate of the small controller box provided with the LED strip, which had 10 microseconds delay between bits, right? So if you consider there were 50 controller chips on the LED strip, and for each frame each chip would receive 24 bits, now each bit would take about 10 microseconds. So if you do the math, you would that would result in 12 milliseconds per frame. And that box would probably run at about 80 frames per second or less, and that's quite enough. Yeah, so that was fun. Maybe I'll do some nice stuff with it, some nice effect or some nice shape for EMF, I have to see. So last and least, 2 upcoming events are the IFConf, which is an online interactive fiction competition. This is a write your own text mode adventure game, or something that looks like an adventure game. I had some ideas for this. I think I talked about this a few times ago, or a lot of times ago, but I'm not going to do anything this time because I have other stuff to do and work as well. So there's that. Another retro challenge. I joined in that last time. It was April. Now it was very nice. That's a online friendly competition to do something with old computer hardware or old computer stuff, or do something with retro technical stuff basically. Now the thing is, I have a difficult time communicating with the guy organizing it, and such a difficult time that if I don't get feedback I'm not gonna compete. If I get feedback I might compete, because there's a lot of effort going into that, and I don't have that much time, so we'll see how that goes. But yeah, no idea. So that was all for now. For more information, links and previous episodes, visit podcast.cba.si. Stay tuned, thanks for listening, and goodbye.